Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and we're in a little mini series within that larger playlist. And I'm calling this mini series Two-Sided Uniformly Most Powerful Test in the One Parameter Exponential Family. And this is part 3. Now in part 1, we listed or showed what the theorem is that makes these a two-sided uniformly most powerful test, and it really depends upon the data follows a one parameter exponential. So here we're going to look at an example where data is normally distributed with mean mu and variance sigma squared. We have a sample size n, but we're going to assume that the mu is known, the mean of the normal is known, and we're going to conduct tests about the variance of this distribution. So the density for a normal distribution, of course, is this. Now it's already sort of in exponential form now, which is it's strictly increasing in this parameter here, right? So for it's increasing in sigma squared, and then also that makes this value the sufficient statistic. So t, the sum of those, is our test statistic. So the hypothesis that we want to test, the two-sided test, is the null is the true population variance less than some value, or is it really greater than that value? And the alternative is it between these values. And as mentioned in part 1, this is really just an extension of the Neyman-Pearson lemma, which is pretty fascinating to me, by the way. The UMP test for this test is this. So our test function it's a 1, which means we reject the null hypothesis if our test statistic is between two critical regions, two values, which makes up our critical region, and we do not reject if the test statistic is less than that C1, or if the test statistic is greater than that C2. And this is it. This is our test. But how do we find C1 and C2? We have what's called two side conditions. Now remember, in the Neyman-Pearson lemma, there was only one side condition. The expected value of this under the null hypothesis was alpha. But here there's two. So the expected value of our test function, given that the true variance is sigma squared 1, which we get from here, that has to be alpha. And then the second condition is the expected value of our test function, assuming the true variance is sigma squared 2, and that also has to equal alpha. So there's two conditions here. So then to find C1 and C2, we just have to solve simultaneous equations. So note that the test statistic divided by sigma squared, which is this follows a chi-square distribution with n degrees of freedom. Now some of you might think, whoa, isn't it n minus 1? And the answer is no, because we know mu. So then it's the degrees of freedom is n. If we didn't know mu and would put an x bar here, the sample mean, then it would be n minus 1. So this is a chi-square with n degrees of freedom. So now the expected value of our test function, assuming the true variance is sigma 1 squared, set it equal to alpha. Now remember, phi is discrete. It takes on this value and this value, 0 or 1. So the expected value of a discrete function is this value times the probability, so that's 0. This value, 1, times its probability. So that's why it's just the probability of our test statistic being between these two cutoff values, under the assumption that the true variance is sigma 1 squared. Now if we divide everything by the true variance, sigma 1 squared, then this piece here follows a chi-square distribution. Now the second condition, the expected value of our test function, assuming the true variance is sigma 2 squared, set it equal to alpha, is this, but remember we're assuming the true variance is sigma 2 squared, and then divide everything by sigma 2 squared, and we get this relationship where this is a chi-square random variable. Now we have to find C1 and C2 that make these two equal alpha. And so what we're going to do is I'm going to show you graphically what's going on, and then we will use R to solve it, because it's just so much easier. But here, so we want this to be alpha, and our random variable is a chi-squared random variable. So if we pick a point here in the chi-square distribution, and we call it chi-squared delta. And what I'm doing there, let's say we wanted a point in the chi-square distribution that the area to the left of it would be, say, 0.05, then we would call that chi-square sub 0.05, because the area to the left is 0.05. But we're going to randomly pick a point, so call it chi-squared delta. Then this point is determined. You have to go along the chi-square distribution until the area to the left of this value, which we'd call chi-square delta plus alpha. So then the probability of chi-square distribution being between those is alpha, right? But there's an infinitely many number of these that we can pick, and then this one's determined because it has to be the point that makes the area under that curve, chi-squared delta plus alpha, right? Because then you subtract the CDF of both and the area is alpha. And we do the same thing here. We're randomly picking values that this is chi-squared, I'm going to call it delta 2, and this one would be chi-squared delta plus alpha. Now here, but we want C1 and C2. So if this one is called chi-square sub delta 1, then we can solve for C1. So C1 is sigma 1 squared times that chi-square random variable. Now this is how we go about it. So let me show a picture of what's going on. So there's some curve, and these are the C1 and C2 that we want to find. So this isn't quite 100% accurate, but I just want to give some sort of graph. So here C1 we said was this value, right? And that's the chi-squared delta. And then the C2 is determined that's the chi-squared delta 1 plus alpha, right? And so we get, for all possible values that we pick for this chi-squared delta 1, we get, an infinite, there's an infinite number of these. Sigma 1 squared is fixed, so there's an infinite number of those. And then corresponding to each point, there's a point C2, so we can graph that. And so what's going on, and this isn't quite right, but we determined this value, and then we have to go over C2 such that it makes an area, what we want. But here, this is what we're doing. So these values, the C1 and C2, create some sort of graph where this is, C1 values and C2 values. And then we do the same thing for the second side condition, right? We're picking chi-squared delta 2s, and then that determines the right point. We have to go over, alpha, or delta 2 plus alpha. Anyway, we get an infinite number of C1, I should probably call them primes, and then this one is determined. And so we get some sort of equation like this. And then the spot where they meet is where we find the C1 and C2 that is this condition. So, but to do this by hand is actually quite tough. So what we'll do is we'll use uniroot in R to find this point. It's very quick too. And so the next video is going to be an R illustration of this chi-squared test and finding the critical regions. And that's it. So I hope you enjoyed this video. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.